Alright, the fourth learning unit is carbohydrates. So the learning objectives of this learning unit are define and classify carbohydrate, explain the concept of isomer, explain and show chirocarbon, distinguishing between the D and L designation of carbohydrates, distinguishing between the alpha and beta hydroxyl group in cyclic hemiacetal, identify glycosides, listing the physical properties of monosaccharides and also giving examples, and lastly giving examples of disaccharides, oligosaccharides and also polysaccharides. Okay, first we go to the definition of carbohydrates. So in simplest layman term, carbohydrates are basically sugar. Okay, so they are polyhydroxyaldehyde or ketone or any substance that yield aldehyde or ketone when they undergo hydrolysis. So carbohydrates are very important in diet for biosynthesis process. Okay, means one of the function is to provide energy. Okay, so besides lipid and protein, carbohydrate also important to give energy. So carbohydrates are divided into 4 groups. Okay, the first one is monosaccharides, second one is disaccharides, the third one is oligosaccharides, and the fourth one is polysaccharides. And we will look into detail of these 4 groups later. So example of food source that are rich in carbohydrates are bread, grains, and also leafy vegetables. So the general formula for carbohydrate is CH2ON. Okay, so the basic composition of carbohydrate is CH2 and then O. So the first class of carbohydrates is monosaccharides. So monosaccharides contain a single polyhydroxyaldehyde or ketone unit. So the word saccharol comes from Greek word which means sugar. So example of monosaccharides are glucose or fructose. Now the second class of carbohydrates is disaccharide. So disaccharide consists of 2 monosaccharides that are linked together by a covalent bond. Okay, example of disaccharide are sucrose. The third class of carbohydrates is oligosaccharide, and oligosaccharide contain from 3 to 10 monosaccharide. Okay, 3 to 10 monosaccharide. So example of oligosaccharide is raffinose. And the last class of carbohydrates is polysaccharide. So polysaccharide contain very long chain, okay, which consists of hundreds and up to thousands of monosaccharide. Okay, and this monosaccharide unit either link in straight, okay, chain or branch chain. Okay, so this one is the branching here, the green color. So example of polysaccharides are cellulose, glycogen, and starch. Next, we move on to the classification of monosaccharides. So monosaccharides are classified according to the number of carbon in the monosaccharide. So if you have 3 carbon altogether, okay, it's called triose. Okay, F4 tetrose, F5 pentose, 6 hexose, and so on. Okay, 7 heptose and so on. Okay, so the presence of aldehyde indicated by the prefix aldo, and if it's ketone we use the prefix ketone. Okay, so means if it has aldehyde, then we call them aldose. If it belongs to the ketone saccharide, we call them ketose. So these are example of aldose, okay, which belongs to the aldose group or belongs to the ketose group. Okay, on the left here, okay, glucose is example of aldose. Okay, whereas fructose here, example of ketose. Okay, so ketose means it has ketone, okay, keto group here. Okay, at C2. For aldehyde, normally it is positioned at one end. Okay, so basically at this end here. Next, we move on to concept of isomers. Now, I'm sure you have basic knowledge of isomer. Okay, so if you have two different compounds having the same number and even the type of atom, okay, and both have same molecular weight, then they can exist as isomer. And this can be represented by using projection formula, okay, so that we can see the three-dimensional structure of these isomers. So this is example of isomers, okay. Glyceridehydride, the simplest carbohydrate. So if you look at these two glyceridehydride here on your left, on the left side here is L-glyceridehydride, on the right is D-glyceridehydride. Okay, so they are both are mirror image of each other. Okay, normally the L type of saccharide has OH group on the left, whereas the D type of saccharide will have OH on the right side. Okay. Next is chirocarbon. Okay, so chirocarbon is any carbon atom connected to 4 different groups. Okay, it has to be 4 different groups, otherwise it is not categorized as chirocarbon. So many organic compounds, including carbohydrates, contain more than one chirocarbon. So look at these examples here. Okay, can you identify which of these molecules are chiral carbon? Remember, the criteria of a chiral carbon, it must have 4 different groups. Okay, so I can give you one example here. Okay, so this is one example of chiral carbon. Okay, it has 1, 2, 3, and 4 different group attached to the carbon. And I can give you one example which is not chirocarbon, which is this one here. Okay, because all of the sites here are similar. Okay, hydrogen. So this is example of saccharide. Okay, monosaccharide to be specific. So can you identify the chirocarbon in this monosaccharide? Okay, normally for saccharide or carbohydrate, the chirocarbon is positioned in the center part. Okay, so here carbon 2 and carbon 3 are chirocarbon. Okay, not carbon 1, because carbon 1 will have 1 H, 1 O, and then another one here. And then so it's not 4 different type of 4 different group. Okay, the second carbon 2 here, yes, it's chirocarbon because 1, this is 1, let me use different color, this is 1, okay, 2, 3 hydrogen here. Okay, let me put this here. Okay, 3 hydrogen, and then 4 this group here. So 4 different group. Okay, so normally in the center. Okay, like this one here, glucose. This is not chirocarbon. Okay, because you only have 1 oxygen, 2, and then 3. Okay, not 4. But this one is chirocarbon. Okay, because it has 1, 2, 3, 4. Okay, 4 different groups on each side. On its side. And you can find the remaining chirocarbon in this monosaccharide. Similarly, for this compound too, okay, you can identify the chirocarbon. Now, what is second rule? When a molecule has more than one chirocarbon, each of these carbon can possibly be arranged in either the right hand or the left hand form. Okay, remember the D and L in the previous slide? Okay, so means there are 2 power of n possible stereoisomer. Okay, so actually this is the formula to calculate the maximum number of possible stereoisomer of any saccharide. Okay, for example, the C6C aldose, okay, aldose, okay, means it has 6 carbon, will have 4 asymmetric center. Remember, the center carbon is chirocarbon, not the n carbon. So means carbon 2 and carbon 3. Okay. Carbon 2, 3, 4, and 5. Okay, not carbon 1 and 6. So that's why it has 4 asymmetric centers. So therefore, 2 power of 4 will give you 16. Okay, 16 possible stereoisomer. So means half of the 16, 8 is the L form, another 8 is the D form. So this is cholesterol structure. Okay, you have go through this in lipid learning unit. Okay, so cholesterol has 8 chirocarbon. Okay, which is dotted in blue color there. Okay, so means 2 power of 8 will have possible of 256 stereoisomer. Okay, in which half of this D, another half is L. However, okay, nature will only make one. Okay, one type. So what is Fisher projection? Okay, Fisher projection is the convenient way for us to represent this mirror image. Okay, the D and the L type. Okay, remember OH on the left is the L type, so you just remember left, L, left. Okay, that's how you remember. Okay, so means the opposite would be D. Okay, so you remember one, then you can remember the other one. Okay, so you remember L because left, L, left. OH is on the left. Okay, this one is another Fisher projection to show you the difference between the D saccharide and the L saccharide. So this is the example, the simplest saccharide, which is glyceraldehyde. Okay, so for sugar, okay, with more than one chiral center, okay, more than one, okay, like glucose here, okay, it has more than one chiral center. Remember, 1, 2, 3, 4, right? 4 chiral center. So we will refer to the farthest OH from the aldehyde and ketone group. So this is the aldehyde group, this is the ketone group. So the OH farthest away from here, which is this one. Okay, this one. So on the right side, so D. On the left side, so L. So most naturally occurring sugars belongs to the D isomer. Again, this is to show you the difference between the D and L. Okay, so D glyceraldehyde, L glyceraldehyde, D erythrose, L erythrose. So glucose is an aldohexose. Okay, remember the prefix just now? Okay, aldo prefix. Okay, and then hexose with 6 carbon. Okay, ribulose is a ketopentose. Okay, because it has ketone group and it has 5 carbon. Okay, pentose. Okay, ketone group. So you should be able now to classify this following monosaccharide. Okay, like the previous slide just now. Okay, count the number of carbon and then look whether it is aldose. Okay, aldose or ketose. Okay, ketose or aldose, and then look at the number of carbon. Okay. So this figure shows the stereoisomer of the aldose. Okay, here the L form is not shown, only the D form. Okay, so means the L form is the mirror image of this D form. Okay, so saccharide belongs to aldotriose. Okay, triose with 3 carbon. 1, 2, 3. Okay, aldo because it has aldehyde group. Okay, we'll have total of 2 possible stereoisomer. Okay, the second hand rule. Okay, only 1 chiral carbon, so 2 power of 1, so 2. Okay, one is the D form, which is shown here, D form. Another one is the L form, okay, which is not shown here. L form means it's the mirror image of this. Mirror image means the OH now is on the left. Okay, second one is aldotetrose, in which it has 4 carbon. Okay, 1, 2, 3, 4. Okay, 4 carbon. And it's aldose. Okay, aldehyde. Okay, aldehyde type of saccharide. Okay, so it has 2 chiral carbon, so 2 power of 2, 4. Okay, 4 total of possible stereoisomers, in which half of it, 2 of it is the D type here, another 2 is the L type. Okay, so the hydroxide group farthest away, okay, from the aldehyde group here, okay, is on the right, so D. Okay, so for the L type means OH is on the left. Okay, similarly for aldopentose here. Next is aldohexose. Okay, so it has 16 possible stereoisomers, in which 8 of shown here are the D type, another 8 is the L type, which is the mirror image of this D type. Now let us look at the family of ketose. Can you identify the difference between the possible stereoisomer for ketose compared to the aldose group just now? Okay, so you can see the number of chiral carbon is less, okay, less compared to the aldose group. So therefore, the total possible stereoisomer will be less too. Okay. Okay, you can say it's less by half. Okay, so for aldotriose, it has 2, right? So ketotriose only have 1. Okay, aldotetrose have 4, but ketotetrose only have 2. Okay, by half. Why? Due to the presence of this keto group on carbon 2. Okay, which makes the chiral carbon even less. Okay, so this is the ketohexose, only have 8 possible stereoisomers compared to aldohexose, which has 16. Now let us look at the chemical properties of monosaccharide. So monosaccharide do not usually exist in solution in their open chain form. Okay, so an alcohol group can be added to the carbonyl group in the same molecule to form a pyranose ring, which contain a stable cyclic hemiacetal or hemiketal. Okay, so this is the pyranose ring. Now, how is this pyranose ring formed? Okay, remember the Fisher projection just now. It looks like the fish bone like this, right? So you just imagine you bend this and you meet with this end here. Okay, you close it up so it becomes this pyranose ring. Okay, so it will form cyclic hemiacetal, either alpha or beta. Okay, so alpha is referring to the hydroxy group pointing down, whereas the beta is where the hydroxy group is pointing upwards here. Okay, this hydroxy group here. Okay, so up is beta. Okay, alpha down. Okay, so you remember, the way you can remember this is using the Malay term, but it's the opposite. Okay, A atas, but instead OH is bawah. B bawah, but instead the OH is atas. Okay, it's the opposite. Okay, that's how you remember it. Now, the cyclization of this glucose will produce a new asymmetric center at C1. Okay, so the two stereoisomer are called anomer now. Okay, anomer, alpha or beta. So mean we have addition. We have addition. Just now we have either D or L, right? So now we have beta or alpha in front of the D or the L. Okay, now we have additional here. Okay, due to the cyclization just now. Okay, so alpha below the ring, beta above the ring. Okay, this OH here. So this representation of the cyclic sugar are called Haworth projection. I'm sure you know about this already. Okay, Haworth projection. Now fructose closes on itself to form a furanous ring. Okay. Similarly, the alpha and the beta also. Okay, so alpha bawah, beta atas. So fructose, okay, can form either the six-member pyranose ring, okay, by the reaction between the carbon 2, okay, this keto group here, with OH on carbon 6. So it becomes six-membered. To become a five-member furanose ring, the reaction is between C2 and OH on the fifth, okay, on carbon 5, okay, carbon 5. So look at these two structure here. Okay, we have ribose and also galactose. So which one is the alpha form and which one is the beta form? Okay, so you should be able to identify which one is alpha now and which one is beta. Look at the position of the OH. And you can draw their anomers. Okay, either the D type or the L type. Monosaccharides can undergo oxidation, okay, in which it can react with Benedict reagent, okay, which is a basic solution of copper 2 plus, to form a red-orange precipitate copper 1 oxide. So basically, all monosaccharides are reducing sugar, okay, because it's able to form this red-orange precipitate with Benedict reagent. Okay, so saccharides like glucose and fructose are example of reducing sugar. Now, the hemiacetal and hemiketo forms of the monosaccharides can react with alcohol to form acetal and keto structures which are called glycosides. And the new carbon oxygen bond is called glycosidic bond. And this glycosidic bond is not having reducing property. Okay, for example here, methanol, okay, alcohol, react with anomeric OH on glucose to form methyl glycopyranoside. So the alcohol, okay, react with the monosaccharide glucose, okay, to form the glycosidic bond, okay. So in this case, it form methyl alpha, okay, di bawah, okay, di glycopyranoside, and also methyl beta atas, okay, glycopyranoside. Okay, so these are the glycosidic bond. Okay, when the alcohol react, okay, with the OH, okay, from the monosaccharide. So these glycosides or the glycosidic bond are not reducing sugar, means it cannot react with Benedict reagent to form the red-orange precipitate. So in these two molecules here, the glycosidic bonds are here and also here. Next, we move on to the physical properties of monosaccharide. So most monosaccharide will have a sweet taste. Fructose is the sweetest, in which it is 73% sweeter than sucrose. Secondly, monosaccharide are solid at room temperature, and they are extremely soluble in water, so you can easily dissolve sugar. So despite of their high molecular weight, the presence of large number of hydroxyl group makes the monosaccharide much more water soluble compared to any other molecule with similar molecular weight. So the amount of glucose that can be dissolved in water to make a syrup is about 1 gram in 1 ml of water. So if you have 20 gram, it should be able to dissolve in 20 ml of water. So this table here shows the sweetness level of different sugar. So sucrose is one, table sugar, table sugar that we used in our daily life will have sweetness level of 1. Fructose is the sweetest, having 1.73 sweetness level. So here you can see galactose, xylose, and also fructose are the monosaccharides. Mean all of these monosaccharides are reducing sugar. So most disaccharide like maltose are non-reducing. Lactose is exception. Lactose is reducing sugar. These three are example of important monosaccharide. The first one here is beta-D-ribose, in which this is the sugar backbone of RNA. The second one is beta-D-galactose. This is incorporated with glucose into lactose. The third one is beta-D-deoxyribose. This forms the sugar backbone of DNA. Next is beta-D-glucose, or also known as dextrose and blood sugar. And this beta-D-glucose are present in honey and fruits naturally. And this type of glucose is metabolized in our body for energy. And the other type of sugar normally are absorbed into the body, but must be converted to glucose, by the liver. The next example is beta-D-fructose, or also known as levulose and fruit sugar. Fructose is the sweetest monosaccharide, with 1.73, almost double the sweetness level of sucrose. So it is present in honey in 1:1 ratio with glucose. It's also present in fruits and also corn syrup And normally, fructose is used to sweeten food because we don't need as much fructose compared to when we use sucrose. Next is example of disaccharide. Okay, so disaccharides are two monosaccharides joined by covalent bond. Okay, or the glycosidic bond. To be specific, okay, so if we look at monosaccharide of glucose with another glucose, okay, in this case is alpha D, okay, alpha D will form maltose, okay. So the glycosidic bond is between carbon 1 from one of the glucose and carbon 4 from the other glucose. That's why it's alpha 1 to 4 glycosidic linkage. Alright, this maltose is also known as malt sugar, and it is found in germinating grains such as barley, and it is formed during hydrolysis of starch to glucose during digestion. Another example of important disaccharide is lactose, or also known as milk sugar. So this is only found in either cow's milk or human milk, and the composition of lactose in human milk is much more compared to the lactose present in cow's milk. And lactose are composed of galactose, okay, joined by beta 1 to 4 glycosidic linkage to glucose. So maltose is alpha 1 to 4, lactose is beta 1 to 4. The third example of disaccharide is sucrose. So sucrose are formed by 1 unit of glucose joined by glycosidic linkage with fructose, okay, to form sucrose. Sucrose is also known as table sugar, and it is abundant in sugar cane and also sugar beets. Maple syrup contains about 65% sucrose along with glucose and also fructose. Now, when you heat sucrose, it will form a solid residue, and that is what we call caramel. Another flavoring agent called invert sugar is produced by hydrolysis of sucrose under acidic condition. It has to be under acidic condition so that it will form the monomers of the disaccharide, which is glucose and fructose. Now, invert sugar is sweeter than sucrose because of the presence of the fructose after the hydrolysis. Now, some of the sugar found in honey is formed in this fashion, and invert sugar is also produced in jam and jelly prepared from acid-containing fruits. Because the main criteria for invert sugar is acidic condition. So if we use acidic fruits, we can form invert sugar already. Moving on to the third class of saccharide, which is oligosaccharide. So it formed from 3 to 10 monosaccharide, and one example is raffinose. So raffinose is found in peas and beans, and it is made from monosaccharide of galactose, glucose, and also fructose joined by glycosidic link. Okay, the last class of carbohydrate is polysaccharide, which contain 100 and up to 1000 of carbohydrate unit, and they are not reducing sugar. And we will focus on the three important example of polysaccharides, which are the polymer of glucose. The first one is starch, second one is glycogen, and the third one is cellulose. Now this table shows the example and the uses of polysaccharide in food. Okay, so you can read through. So the first type of polysaccharide is starch. So starch is a polymer consists of the D-glucose unit, and they are usually insoluble in water due to their high molecular weight. Okay, because the polysaccharides is made of hundreds up to 1000 monomers of monosaccharide. Okay, and they can form thick colloidal suspension with water. So unlike the simplest sugar, they readily dissolve in water. Okay, but for polysaccharide, they form thick colloidal suspension with water. So there are two forms of starch. Okay, either amylose and amylopectin, and we will see the difference between these two in the following slides. Now, the most important food source of starch are rice, corn, wheat, potatoes, tapioca, and many more. So let us look at amylose. So amylose consists of long, unbranched chain of glucose only. Okay, from 1000 to 2000 molecules of glucose connected by the alpha 1 to 4 glycosidic linkage. And in plants, okay, the starch form is 10 to 20% is amylose. The remaining is amylopectin. So these amylose are the one responsible to give the blue-purple color in the presence of iodine. So that's why when you do experiment, okay, to detect the presence of starch, you use iodine. So if the iodine does not change color to blue-purple color, means very small amount of amylose present. Okay, so this is the basic structure of amylose. Okay, built of glucose monomers. Okay, joined by the alpha 1 to 4 glycosidic bond. Okay, straight chain. So the second type of starch is amylopectin. So the amylopectin is, besides having the long chain, straight chain, okay, it also have branch. Okay, so the straight chain is connected by the alpha 1 to 4 glycosidic link, and the branch is alpha 1 to 6. Okay, and this branch form every 24 to 30 glucose unit along the chain. So if you have the straight chain here composed of the monomers monosaccharide of glucose, so when you have 24 to 30, then it branch. Okay, it branch. Okay, so 80 to 90% of starch in plant is in the presence is in the form of amylopectin. Okay, this shows the structure of amylopectin, where you have the straight chain of glucose units here, okay, joined by the alpha 1 to 4 glycosidic link, and every 24 to 30 monomers of glucose, it branch up here, okay, from the alpha 1 to 6, okay, branching point, okay. Okay, 1 to 6 means carbon 6 here, okay, carbon 6 here, okay, 1 to 6. So this is carbon 1, this is carbon 6. Okay, let me use different color. Carbon 1, carbon 6. Okay, that's why it's alpha 1 to 6. So the second type of polysaccharide is glycogen. Okay, so starch is plant starch, glycogen is animal starch. Okay, the structure is similar to amylopectin. It has both alpha 1 to 4 glycosidic linkage and also alpha 1 to 6 branch point. The difference is that glycogen is even more highly branched, okay, and this branching will occur every 8 to 12 glucose unit, unlike amylopectin 24 to 30. Okay, glycogen even less, 8 to 12. Okay, so that's why it's highly branched. So glycogen is abundant in the liver and muscle. Okay, upon hydrolysis, it will form glucose, okay, which maintain normal blood sugar level and give or provide energy. So the third type of polysaccharide is cellulose. Okay, cellulose is a polymer consists of a long unbranched chain of D-glucose connected by beta-1 4 glycosidic link. So the difference between cellulose and amylose is the linkage here. Okay, they are both straight, okay, straight chain or unbranched chain, but they are joined by different glycosidic linkage. Okay, amylose is alpha 1 to 4, cellulose is beta 1 to 4. So it may contain from 300 to 3000 glucose unit in one molecule of cellulose. Okay, the last part is artificial sweeteners. Okay, now the difference between artificial sweeteners and the other 4 classes of carbohydrates is that artificial sweeteners are non-calorie. Okay, means they don't have calorie. Okay, but the sweetness level of this artificial sweeteners is very higher, very much higher compared to the monosaccharide and even the disaccharide. Okay, for example, saccharin. Okay, saccharin is 500 times sweeter than table sugar. Now, this artificial sweetness is actually found by accident. So it's coincidentally found by chemists during reaction. Okay, so the chemist is actually want to produce something else, but during the process he smoked cigarette, and his cigarette butt is mistakenly put on the compound that he synthesized, and when he continued smoking, he tastes the sweet, okay, the sweet level, okay, of the compound that is stuck on his cigarette butt. So it's actually found by mistake, okay, and it's actually commercially marketed for diabetic patient because it's non-caloric. Okay, however, it was banned in some area for some time because it was suspected to be carcinogen. Okay, but nowadays it is approved to be used in food products. So you can actually find many food products now uses artificial sweetener. One is because they can market their product as non-calorie, okay, for those who are going for diet uh, routine, okay, but they want to enjoy sweet taste also, okay, even though this sugar is actually designed for diabetic patient, but it's many products now uses artificial sweeteners. Okay, another reason why they use this is because they can reduce or cut costs in production, because they don't need to use much sweetener, because the sweetness level is 100 times more than the table sugar. Aspartame is another example of artificial sweetener, okay, widely used also in product nowadays. The sweetness level of aspartame is about 160 times sweeter than sugar. Acesulfame K is another one. Okay, so it's approved by the FDA in 1988, in which it is 200 times sweeter than sugar. It is non-caloric. I mean, it is not absorbed by the blood, so means when you consume, it's immediately discrete out of the body. Okay, secreted out of the body. Okay, sorry. It is heat stable and also can be used during cooking. So next one is sugar alcohol. One example of sugar alcohol is sorbitol. Okay. So other type of sugar alcohol, normally if you find the word all, okay, ending with the word all, like mannitol, okay, xylitol, okay. So these are example of sugar alcohol. Okay, this kind of sugar, they are slowly absorbed, okay, and also can be used as a sweetener in diabetic food. Okay, it has lower calorie. Okay, it still has calorie, but lower calorie than other carbohydrate, and used commercially in sugar-free candies, in cookies, in chewing gum, okay, and many more products. Okay, toothpaste also. Okay, so that's why you can have that sweet taste also in your toothpaste, okay, due to the presence of the sugar alcohol. Okay, the last one is sucralose. Sucralose is another non-caloric artificial sweetener approved by the FDA in 1998. Now the glucose in sucrose is replaced by a galactose, okay, and 3 of the OH group are replaced by the Cl atom here, okay, Cl atom, okay. So this molecule will still taste sweet, but not metabolized in the body. So it's secreted out from the body, okay, not being absorbed by your blood. So that concludes the first part of carbohydrate.